Today we will consider in detail the case where M is in B of H, a von Neumann algebra, with psi naught in H, a bicyclic vector, I denote by phi the vector state omega psi naught restricted to M. Well, and now let's consider the operators S naught with domain M psi 0, taking an x psi 0 into x star psi 0 in H. And also the operator called F0 from the commutant M prime psi 0, taking an x prime psi 0 into x prime star psi 0 belonging in H. And then we saw already the following computation, the fact that S naught of x psi 0 times x prime psi 0, it's equal to f of x prime psi 0 times x psi 0. It's obvious that here you have an x star, here you have x prime star, and x and x prime commute. Well, this means the following thing, that the operator S naught is included in the dual, in the adjoint of the operator F naught, so that it follows that SO is pre-closed or closable, because every adjoint is closable. Okay, then the same way we see that F naught is included in the dual of S star, so also F naught is closable, and we denote by S the closure of S naught, by F the closure of F naught, and we still have these relations, so that we can say S is equal to its restriction to M psi naught closed, and on M psi naught it acts like there. This is also F restricted to M prime psi naught, and we still have this relation. S is included in F star, and F is included in S star. We will see that in this case of a bicyclic vector, we have actually equalities in here. So that I will not prove it now, but I just announced that we will have equalities. Now, another thing which is obvious from the definition of S is that S naught square is included in the identity. If you make x star star, you get x. And so that, because S is the closure of S naught, it follows that also S naught is included in the identity. And from this, it follows that S is equal to S minus 1. Okay. Consider also the operator delta, which is S star S. This is a linear operator, not a conjugate linear operator, because it is twice conjugate linear here. And by a theorem of von Neumann, this is a self-adjoint operator, positive self-adjoint operator, and S restricted to the domain of delta is recovered by its restriction to to the domain of delta. So I put von Neumann here. And with this, we have also the polar decomposition. Polar decomposition, which is S, it's equal to J delta to power 1/2, where J is a surjective isometry because S is invertible, and so delta is a positive self-adjoint operator and also is a non-singular operator. Now, once we have this thing, we have the fact that S is equal to S minus 1. So S is J delta power 1/2. S minus 1 is equal delta power minus 1/2 times J minus 1. And from this, what we get that delta minus 1/2 it's equal J delta 1/2 J. We just put the J from here, you put it here. Okay? And I can write this as the following, as J square times J star delta 1/2 J. Now, by the uniqueness of the polar decomposition, it follows that J square is equal to the identity, and delta minus 1/2 it's equal to J star delta 1/2 J. But from here, we have J square is equal to the identity. We have also J star it's equal to the identity. So we have also J is equal to J star. It's equal to J minus 1. And delta is a linear operator, while J is a conjugate linear operator. So that these properties of a conjugate linear operator means that this is a conjugation on the Hilbert space H. Okay. Now, let me put also the following thing. S is equal J delta 1/2, which due to this relation in here is delta minus 1/2. J minus 1 is equal to J. So that this is delta minus 1/2 times J. And it's important to notice that in this, the domain of S is equal to the domain of delta power 1/2. S star, the same way, is J delta minus 1/2 is delta 1/2 J, and the domain of S star is equal to the domain of delta minus 1/2 in this. Another thing that it's good to have from the beginning is the fact that, of course, S of psi naught means S of 1 times psi naught. So it's 1 star psi naught, so this is equal to psi naught. And if I put here S star as psi naught, I get an S star here. The same way, this is equal to psi naught. So that what I get is the fact that delta psi naught is equal to psi naught. And then, by functional calculus, it follows that for every power, delta to power alpha of psi naught is equal to psi naught. Now, once we have that delta of psi naught is equal to psi naught, so that we have that delta 1/2 of psi naught is equal to psi naught, from this relation in here. We put it in psi naught, this is in psi naught. So it follows that also J of psi naught is equal to psi naught. And this is good to have from the beginning. Okay.
That equation.
Sorry?
In the right-hand side equation, that delta minus half equal to j delta square delta half j.
Inclusion? Where inclusion?
Equation. Second line. How did you get j square is 1?
No, I don't get the question.
He's asking about the second line. Second line, the j he writes j star then.
Why? Unless you have. No, how did you write that j square j star delta of j?
Okay. So you question this equality here?
No,
Yeah?
above the two lines, second one.
Here?
He's putting a j star.
Okay. J star is equal to the identity because of the fact that it is, well, it is conjugate linear, but it is a partial isometry whose support is the support of S, the right support of S. And the right support of S is the identity. So that I have J star, it's equal to the identity, right? This was the question? Okay, fine. No, because S is a invertible operator. Okay, and let's go a little bit further. And notice that we have the following thing. J delta J, it's equal to delta minus 1. And J lambda delta J, it's equal lambda bar delta minus 1. Lambda bar J delta J lambda delta minus 1. And this means that for every Borel function, we have that J f of delta J is equal to f conjugate of delta minus 1. So once we have these two obvious relations, we get, by passing to 1 plus delta to the power minus 1, which is a bounded operator. Then you do the functional calculus for it, so that, so these are the, in particular, we have that J power delta IT, it's equal to delta IT J. It's a particular case of this formula and of the fact that J squared is equal to 1. And it remains just to make a statement, the Tomita's theorem. Oh, the statement is very simple. J, Mj, it's equal to M prime. And delta power IT, M delta power minus IT, is equal to M for every t. And the purpose of today's lecture is to give a proof of this Tomita's theorem. The proof I will present is the proof due to Alphonse van Dahl. And it appeared in early 70s, in 71 or something like that. Okay, it's a short proof, a very lucid proof. And we will go now to see it. See, once you have the result of the two-meter theorem, J is equal M prime, you get immediately that J of M psi naught is equal M prime psi naught. So that let us say that J is a perfect bridge between M psi naught and M prime psi naught. What we will do, we will construct a very primitive bridge between M psi naught and M prime psi naught, a Wood bridge, say. Namely, we will prove first the following lemma due to Sakai. It is a Radon-Nikodym type theorem. If you have the von Neumann algebra and you have phi, psi, two positive normal forms on, and you assume that psi is less than phi, and also consider a complex number such that lambda plus lambda bar is equal 1, so that the real part of it is equal to 1/2. Okay. Then there exists an operator A in M between 0 and 1, and such that we have psi of x is equal phi of lambda AX plus lambda bar XA. This is a rather easy statement of the Radon-Nikodym type, because it will be essentially an application of the Hahn-Banach theorem. Namely, we consider the set X, it's equal to all the functionals of the form phi of lambda A dot plus lambda bar dot A, when A is a self-adjoint operator and the norm of A is less than or equal to 1. And we want to show that psi belongs to this set, so that we want to prove this statement, but in a weaker form with a self-adjoint operator instead of a positive operator. Now, in order to show such a thing, we notice that this set is a closed convex set, so that this is the variable. So that it's a closed convex set, and if I don't have psi belongs to this one, I will get a functional separating this. Sorry? No, I will explain. I will explain immediately this. I will get continuous linear functional which separates these two things. Continuous with respect to what? Continuous with respect to, look, you have M, the von Neumann algebra, and you have its pre-dual.
So you are assuming that psi is not there in the set.
Hmm?
Yeah. Yes.
Okay, and the dual of the pre-dual, it's equal M. And the V topology is equal to weak topology sigma M, M star. So that if we restrict this thing to the Hermitian part of the von Neumann algebra, the self-adjoint part of the von Neumann algebra, what we get by the Hahn-Banach theorem, we get a functional. That means we get an element in M, so that if psi doesn't belong to X, then there exists an element B in M, self-adjoint because I restrict to the self-adjoint elements, and also a number T, a real number, such that I have psi of B is bigger than T, while all these things are less. So that means psi phi of lambda AB plus lambda bar BA is less than T for any A is equal A star, and the norm of A is equal to 1, or less than 1. Okay. Now, for this B, I take the polar decomposition. Then, in this polar decomposition, we will see that the isometric part here, partial isometry here, is self-adjoint. And, of course, it's less than 1. And then B, it's equal to VB, it's equal to V star V. If I put a V star here, V star V leaves B in peace. But V is equal to V star because the element B was self-adjoint. So this is equal to VB, and also it's equal to BV. Okay. Why? Simply because from this, by adjunction, I get this. Just taking the adjoints in here. Okay. Now, we get the following thing, that T, which is less than psi of B, is less than or equal to psi of B, because psi is a positive form, and of course B self-adjoint is less than the absolute value of B. And this is less than phi of B, because by assumption psi is less than phi, and this is equal to phi of lambda VB plus lambda bar BV. Why? Because lambda plus lambda bar is equal to 1, and VB is equal to BV. So that's what we get here. We get BV or VB, which is the absolute value of B. Okay, and now, by the application of the Hahn-Banach theorem and the fact that V is self-adjoint and of norm equal to 1, it follows that this is less than or equal to T, which is a contradiction.
Is there two factors of it? Sorry, I didn't understand that equation.
This equality? Yeah. You have here B is equal VB is equal BV, and lambda plus lambda bar is equal to 1. So that what I get here is modulus of B, here is modulus of B, common factor, lambda plus lambda bar is equal to 1. Fine, thank you. Okay. So that this is a contradiction, so that it's true that we have indeed an element A1 is equal A1 star of norm of A1 less than or equal to 1, such that psi of x it's equal to phi of lambda A1x plus lambda bar x A1. Fine. Now, and this happens for every x in M. There is. Now, let's do the following thing. Let's compute psi of A1 negative part, because A1 is written like as A1 plus minus A1 minus. Further decomposition of it. Psi of A1 minus is equal to phi of minus A1 minus square. And this will be equal to 0. Why? Because this is bigger than 0, and this is less than 0. Both phi and psi are positive, right? Psi is positive, so this is positive. Phi or phi is positive, so that this is negative. Consequently, this is equal to 0. So that while we have phi of A minus 1 minus is square, it's equal to 0, then we get that phi of A minus x is equal to 0 for every x. This is by Cauchy-Schwarz. And consequently, if you write here A1 is equal A1 plus minus A1 minus, each time that A1 minus appears, it disappears because phi of that things is equal to 0. Consequently, if I take A is A1 plus, this is a positive element. Because A1 was a norm less than 1, this is less than 1. And we have psi of x is equal phi of lambda ax plus lambda bar xa. And that was what?
A1? Hmm? Would that be an A1 minus?
Yes, is A1, thank you. Is A1 minus. Because you have this thing. So that's the lemma of Sakai, which will be used by Van Dahl. It's completely proved. Now, with this lemma, we will construct that primitive bridge. And this is the following thing. Another lemma, this time of Van Delle, so everything is from Van Delle now. For omega, a complex number of modulus 1, but omega different from negative 1, we have the fact that delta plus omega minus 1, so this exists, of course, because omega is different of minus 1 and of modulus 1. M prime psi naught, it's included in M psi naught. So you see now this provides a bridge between M prime psi naught and M psi naught. Okay. In order to prove this, it is sufficient, it is enough to show the following thing. Consider A prime in M prime, A prime between 0 and 1, and what we have to show that delta plus omega minus 1 of A prime psi naught, that this belongs to M psi naught. That means instead of an arbitrary element in M prime, it's sufficient to take a positive element between 0 and 1, which is obvious. Okay, now we will consider, proof, we will consider lambda is equal to 1 plus omega to minus 1, which belongs to C, and lambda plus lambda bar is equal to 1. Consider now the forms phi and psi in M star in the predual, positive forms. They are vector forms defined phi of x is equal x psi naught psi naught, and psi of x is equal x psi naught a prime psi naught. It is obvious that both functionals are positive functionals because a prime is in the commutant. Maybe it's better to see the following thing. We can write this as being x to power 1/2 a prime x to power 1/2 psi naught. Psi naught. And so for x positive. So that you see immediately from here that this is bigger than 0, and because a prime is less than 1, also is less than this form here, right? Fine. So we have indeed that 0 is less than psi is less than phi, and we apply the Sakai's lemma, and we get an element A in M, 0 less than A less than 1, such that we have the following thing. Well, such that we have what is written upstairs, but I will do it specifically here, namely x psi naught A prime psi naught. This is psi of x. This is equal to phi of lambda ax plus lambda bar x plus lambda bar xa, which is equal to lambda ax psi naught psi naught. This is because of the definition of the function phi, plus this is a psi naught, a psi naught. Okay, so this a remains here for psi naught, and I take the other ones. It's lambda, which I put it in the other side, and also x in the other side will be x star, psi naught. Okay. Okay. When that means, I made a jump in here. That means the following thing. Let me write it here. It means that x psi naught times a prime psi naught minus lambda bar a psi naught, it's equal to lambda bar a psi naught s x psi naught. And we look at this equality in the following manner. X psi naught is something arbitrary in the domain of S. And then what we have here is this psi in the domain of F times this vector, put zeta for it. This is equal to this vector, put eta for it, times S of psi. And this is true for every psi in the domain of S naught. That means in the domain which is enough to recover S. This is an equality which says something about the adjoint of S. And namely, what it says that eta belongs to the domain of S star, and S star of eta is equal to zeta. Now, let's write this. This was just a notation. So that what we get, A prime psi naught minus lambda bar A psi naught is equal S star of lambda bar A psi naught. This is with eta and zeta, which is this is lambda comes out without the bar, S star, A is positive. So I can write instead of A, I can write A star. And if I write A star, I can put S of A psi naught. It's the same as A psi naught. But, OK. So that this is lambda delta A psi naught. Fine. This means that the following thing, that A prime psi naught is equal to lambda bar plus lambda delta A psi naught. And this is equal to delta plus omega times 1 plus omega to minus 1. This is an elementary computation. A psi naught. That means what we have, it is that delta plus omega minus 1 of A prime psi naught, it's equal to 1 plus omega to power minus 1 A psi naught, which indeed belongs to M psi naught. And that's it.
Sorry, one silly question. Why is A psi naught in the domain of delta?
What?
Why is A psi naught in the domain of delta?
Why is this one, right? In
A
the,
psi naught.
A is I not domain of A.
First
here.
First line.
Simply because it was this was in the domain of A star, of S star, because of this thing, because of the computation there. This was in the domain of S star, and what I get this thing without an S. But on the other hand, A psi naught is the same as A star psi naught. And so I can write, instead of A psi naught, I can write S A psi naught. And this is the delta operator. That's yeah. Because it's self-adjoint, I can write S of A psi naught is equal to A psi naught. So that this is OK. Now, the last thing before the big shot is another lemma, which is an approximation lemma. So the approximation lemma is the following. Let psi be an element of the domain of delta 1/2 intersection with the domain of delta minus 1/2. So there are plenty of such elements. All the elements which are in the circle of delta. Okay, and then there is a sequence psi n, which is in psi n belongs to delta plus 1 to minus 1 of m prime psi naught, so that this is already in m psi naught. And these elements will then be in the domain of delta 1/2 plus the intersection, the domain of delta minus 1/2. So there exists a sequence of the form which is assured here to have this inclusion, such that we have the following approximations. We have psi n converges to psi, then delta 1/2 psi n converges to delta 1/2 psi, and delta minus 1/2 psi n converges to delta minus 1/2 psi. Now, let's show this existence of that sequence. Well, we have the following thing. We have j delta minus 1/2 of m prime psi naught is equal S star is j delta minus 1/2 m prime psi naught, and S star of m prime psi naught is f of m prime psi naught, which is equal to m prime psi naught. And this one, this is dense in H. As J is a conjugation, it follows that also this portion is dense in H. So that we can find elements in here, namely, we can find elements eta n belonging to m prime psi naught, such that delta minus 1/2 of eta n converges to a given element in the Hilbert space. The given element in the Hilbert space I want to be delta 1/2 psi plus delta minus 1/2 psi. And then consider also psi n, which is 1 plus delta to power minus 1 of eta n, which is 1 plus, which belongs to 1 plus delta minus 1 of m prime psi naught, which is included in m psi naught because of the previous lemma. Okay, because of this lemma here. Okay, now.
And you said it was Pimsner?
Sorry?
You said Pimsner?
Pimsner?
Previous lemma.
No.
Oh, previous lemma, sorry.
No, previous, exactly. Okay. Now, notice the following thing, that psi n belongs to m psi naught, which is included in the domain of S, which is the same as the domain of delta 1/2. And on the other hand, M prime psi naught is included in the domain of S star, which is the domain of delta power minus 1/2. That means the following thing. It means that psi n is equal to 1 plus delta to power minus 1 of eta n belongs to, it's equal to, now this is something like adding fractions. This delta minus 1/2, 1 plus delta minus 1, delta minus 1/2, eta n. Well, to justify this equality, just put instead of delta a positive number t, and check that 1 over 1 plus t is equal to t power minus 1/2, etc. And so this is by functional calculus afterwards. So it's a trivial thing. And also psi n belongs to the domain of delta minus 1/2. Okay. This one belongs to the domain of minus 1/2, since the operator delta minus 1 times, I'm sorry, here is minus 1, please correct. So the operator delta minus 1, 1 plus delta minus 1 to minus 1 is a bounded operator, because the function t over 1 plus t is bounded. Okay. Now, with this thing, we have the following. I have psi n is equal to 1 plus delta to power minus 1 of eta n. This is delta power 1/2, 1 plus delta to power minus 1, delta minus 1/2, eta n. There is no trick here. Delta 1/2 and delta minus 1/2, they cancel each other. And I can put delta minus 1/2 of eta n because I saw that the eta n is in M prime psi naught. Okay. And this converges to delta to power 1/2, 1 plus delta to power minus 1, delta to power 1/2 psi plus delta to power minus 1/2 psi. Because eta n was converging to this, and this operator is a bounded operator. So that I have this convergence, and now I have just to check that this is equal to psi. Root of t, 1 plus root of t minus 1, root of t, plus the same thing without the roots, will give exactly 1. So that we get the, let me do it completely. Root of t over 1 plus root of t times root of t plus 1 over root of t. Okay, this is 1 over 1 plus root of t. Root of t with root of t cancels, and here I have t plus 1. Sorry. Yes, but Yes. Yes, it's 1 plus root of t. Sorry. And this is 1. No.
Why that sequence converts to there? Can you tell me again?
Sorry?
Why that sequence converts to there?
Why this? Because eta n was chosen such that.
That converts to there, but there is some unbounded operator in front of that. It's a bounded
Well,
operator.
why I have here the convergence? Because this is a bounded operator. That's all. But I choose the eta n to go to this. So that the first assertion here is checked. The other assertions are checked completely similarly, so I will not write again such things on the blackboard. So that also this approximation lemma is okay. And now we go to the main thing. The main thing is the following assertion. We can write proposition or lemma, it doesn't matter. It's the following thing. You take x prime in n prime. Omega, a complex number, the modulus of omega is equal to 1, but omega is different from -1. And what we show the following equality. X prime eta times zeta, I will say immediately what are eta and zeta, is equal to j x star j delta -1/2 times delta 1/2 of zeta plus omega times the scalar product of j x star j delta 1/2 eta times delta -1/2 eta zeta, and this happens for every eta. Huh?
Is there an eta missing in the second class?
So here is eta, here is missing eta. Thank you. That was the question. Okay. Thank you. So for eta and zeta belonging to the domain of delta power 1/2, intersection domain of delta -1/2. Well, in order to prove this, let's first see. We have an x prime in n prime, which is, everything is defined in here. What is x? I have to check also what is x. What is x? I missed to put, this thing is delta plus omega to -1 of x prime psi naught is in here, so it is of the form x psi naught. This is x, right? And now everything is defined, I hope. Jx star j, so that with any x, for any x prime in m prime, any omega in c, and correspondingly x, like in according to this lemma here, I have this equality. Now, I can erase the third lemma in here, because this means simply that instead of eta and zeta, I can consider elements from here, right? Because they approximate everything. Xi tends to xi, delta 1/2 of xi tends to this, and this tends to this. So that if I prove it with elements, say, eta n, zeta n from here, then going to the limit, I get eta and zeta, right? So that this was the role of the third lemma in here, and so that I can get rid of this lemma in here. Okay. So that instead of this, I will take eta is equal delta plus 1 to minus 1 of y prime xi naught, which is in m xi naught, so that this is of the form y xi naught, right? It's existent. And also the element zeta, it's delta plus 1 power minus 1 of z prime xi naught is equal to z xi naught. And now I have, of course, y prime, z prime are in m prime, and y and z are in m. This comes from the notation. Now, I have x prime psi naught. It's equal delta x psi naught plus omega x psi naught, just because the fact that x psi naught was delta plus omega to minus 1 of this thing in here, right? Okay, this is equal to delta means s star s of x psi naught plus omega x psi naught. Okay. Now, because of this, we have the following thing. We have that x prime eta zeta, it's equal to x prime y zeta naught z zeta naught. This is just because eta is y zeta 0 and zeta is z zeta 0 in there. Okay. And after that, this is equal to y x prime zeta 0 is just a simple commutation.
What happened to the delta plus 1 inverse?
I'm sorry?
You have a delta plus 1 inverse. Eta equals delta plus 1 inverse.
Ah, yeah, exactly. It's delta plus 1, I'm sorry.
Where did that go here?
Z and y are defined by these equalities.
Yeah, but here there's no delta plus 1 coming.
Okay, excuse me then. Excuse me, thank you. Okay, now, what I have here, I commuted the two elements z psi naught. Okay, this is equal to y s star s x psi naught times z psi naught plus omega times y x psi naught z psi naught. Okay. This is the fact that This is the fact in here. Right. Okay. And now I go plus this thing. I go, this is equal to again to S y star z psi naught I will show you immediately. Y goes the other side as y star, and then S go to the other side like S, but we change the order in the scalar product because it is conjugate linear. So that S y star z times S x naught, because this remains here. The others went plus omega y x naught, xi naught, z psi naught. This remained unchanged, and will remain unchanged is equal to further to, this is z star y, these are elements in M. S makes the adjunction, and this is psi naught. Here is x star psi naught plus omega y x psi naught times z psi naught. But we want to get back to the elements eta is equal y psi naught, and zeta is equal z psi naught. Okay, so that for this thing I take the element in here, this one in here. It's equal to y psi naught zx star psi naught. It's equal to y psi naught times S of x z star, right, psi naught. Okay, it's equal to y psi naught times Sxs z psi naught. That's obvious, because z star psi naught is S of z psi naught. Okay, and then this is further equal to y psi naught times delta minus 1/2 jxj y psi naught j delta power 1/2 z psi naught. Why this? Because S is equal j delta minus 1/2 or delta minus j delta 1/2 or delta power minus 1/2 j. Okay, I got in this thing. Then it's equal to, this is equal to j x star j delta minus 1/2 j x star j delta minus 1/2, correct, y psi naught, and delta 1/2 z psi naught. Simply I transported everything in the other side by adjunction. And by adjunction, because I have twice j, it changes the order twice, so I get a normal thing. Okay, and I'm still not happy with this. I shall write it in the following manner: j x star j, delta power minus 1/2 eta, delta power 1/2 zeta. So I achieved the goal to go back to these elements. And you can see these elements appearing in here somewhere, I think right here. Jx star j, delta power minus 1/2 eta, delta power 1/2 zeta. Now, the same thing happens also with the second term. I will not write, it's written in these pages. The same thing happens with the other term in here. Okay, and this proves the proposition in here. Now, a completely separate thing, a theorem in single operator theory, which says the following thing. The theorem is a theorem, everything is of Van Delle, so that you have A and B non-singular positive self-adjoint operators, densely defined, in a Hilbert space H. You have also a complex number omega of modulus 1, which is not minus 1. Take x, y, two elements in B of H, and assume that the following holds: x eta zeta, it's equal to y b to power minus 1/2 eta times a to power 1/2 zeta plus omega times the product y b 1/2 eta times a minus 1/2 zeta. That this happens for all eta and zeta in the, let's take it easy, for all zeta in the domain of a to power 1/2 intersection domain of a to power minus 1/2, and eta in the domain of b to power 1/2 intersection domain of b to power minus 1/2. Look in this. Sorry? No,
this is delta plus 1 and this is delta plus omega.
Is delta plus omega in the.
But both are delta plus omega?
Here is delta plus omega in
And
it.
the first one?
Where?
Left side. Eta equal to delta plus 1.
Of course. The same thing, thank you. It's the same thing.
Same equation.
Yeah, of course. Now look at the condition put there and at what we got here. So what we got here, we got something with this element here in the role of y in there. Okay. Then the conclusion is that y is what I will call phi sub omega of x. and this is equal to integral from minus infinity to infinity of omega to power it minus 1/2 over e to power pi t plus e to power minus pi t, a to power minus it, x, b to power it, dt. I will postpone for tomorrow, say, or for the afternoon, the proof of this theorem. It's a very easy proof, in spite of the scaring aspects. It's a very easy proof, which is based on the residua theorem, simply. Okay, I will write also a corollary for this. The corollary is the following. In the same situation, we have a to power...
What is the denominator?
Sorry?
E power what? I can't see from. E power pi t?
This is a to power minus it, x, b to power it.
Exponential term in the denominator.
In here you mean?
Denominator e power
Pi t.
pi t.
E to power pi t plus e to power minus pi t is this. It is a normalizing factor for our integral to be 1. Yeah, okay. The second thing is, under the same assumptions, we have a to power 1/2 a plus omega minus 1. It's equal to integral from minus infinity to infinity of omega to power it minus 1/2 over e to power pi t plus e to power minus pi t, a to power minus it dt. The proof of the corollary is a particular case immediate of the theorem. Namely, you take in the theorem b is equal to 1, to identity operator, and x is equal to 1, and y is equal to a to power 1/2 a plus omega to power minus 1. And it's easy to check that for every zeta in the domain of a to power 1/2 and the domain of power minus 1/2, you have the following relation: eta zeta is equal to y eta a to 1/2 zeta plus omega y eta times a to power minus 1/2 zeta. I repeat, for every zeta in the domain of a to power 1/2 and zeta in the domain of power a to power minus 1/2. This relation is checked immediately, and it has exactly the sense of here, and you get the conclusion as a particular case of the theorem. So I said I will prove this theorem in a quarter of an hour in some afternoon, or maybe this afternoon. It's not more than a quarter of an hour. But now I want to go further to take advantage of this. So looking at here and taking into account this theorem, we get the following thing. We started with arbitraries x prime in m prime, omega a complex number of modulus 1, but not minus 1. And we obtained this relation in here, where x is given by the equality x prime zeta 0 is equal delta plus omega x zeta 0. Now, take an arbitrary y prime in m prime. Then, we use this theorem. From this theorem, it follows that j x star j is equal to integral minus infinity to infinity of this thing. I will not repeat this normalization factor here. Of this thing, delta to power minus it, x prime, delta to power it, dt. So that what we get in here, we get that x star is obtained by putting j both sides. So I multiplied by j both sides, and I got this equality. And now what I get is x star y prime psi naught is equal to the integral minus infinity, this normalization factor, j delta minus it, x prime, delta power it, j y prime psi naught dt. Now I can erase everything in here. And using the corollary in here, we get the following thing. We get that x star y prime psi naught, it's equal y prime x star psi naught. It's equal to y prime s of x psi naught. It's equal to y prime, instead of s, I write j delta power 1/2. And instead of x naught, I put delta plus omega to power minus 1 x prime psi naught. And now here I use the corollary, and what I get is again integral from minus infinity to infinity, the same factor, normalization factor, y prime j delta to power minus it, x prime psi naught dt. Well, now looking at both results, and to the function f of omega equal to, by definition, integral from minus infinity to infinity of the normalization factor, I will write it now, omega to power it minus 1/2 over whatever is in here.
How do you get these two expressions?
How do I get what? This one?
This and the previous. Those two expressions, how do you get? Using what?
Okay. Well, this thing here is a consequence of this. It's an obvious. It's just I applied this in the vector y prime psi naught. Now, what I got here, before I had jx star j is equal to this as a consequence of the theorem. Because in this equation, well, it is, yeah. It's no more on the blackboard, I think, this. No, this is from the theorem. It has nothing. It was the specific thing which was obtained there. and the place of y was played by j x star j. So that this is a consequence of the theorem. Okay, now consider this function. Here is j delta power minus it x prime delta power it j y prime psi naught minus y prime delta to power minus it x prime psi naught. If you look now at this fact that this is equal to 0, is what we, okay? So I put also this thing in there. What is the issue? This is an analytic function in omega. This analytic function in omega extends from the circle minus, without the minus 1 point, extends to all the plane without this line. So that it is valid here for a positive omega. If it is valid for a positive omega, this means simply that the Fourier transform of this function in here over the normalization factor is equal to 0. If the Fourier transform is equal to 0 by the uniqueness theorem in Fourier analysis, it follows that this is equal to 0. So this function is equal to 0 because what is here, it doesn't matter. So that what we get this equality in here. Okay. So that we get this equality, and now we exploit this equality. Yes, I have 5 minutes more, so that I will exploit this equality. Namely, I will take x prime, y prime, z prime in m prime. And what I will put instead of y prime, I will put here y prime, z prime. It's again an element in m prime, right? It's the product. Okay, it will be y prime times z prime times this thing, right? But now, using the original formula with only one element in here, this can be written as y prime is y prime, and this is j delta to power minus it x prime delta to power it j z prime j z prime psi naught. Now look what happens. This element and this element here, these two elements coincide. No, let's put otherwise, up to here only. These two operators is this one and the operator in here, this one and this one. These two operators do commute because this equality of commutation is valid on a dense subset, which is m prime psi 0. So that what we get that we get the commutation of these two things, and because y prime was arbitrary, what we get is j delta power minus it, it was here first, x prime delta power it j. This belongs to m second. That means this belongs to m. So you feel now that it's almost okay, because if you put here t is equal to 0, you get j x prime j belongs to M, which is already a half of the implication j M prime j is included in M, right? So I have to show also the converse thing. And this will be obtained easily. So I beg for 5 minutes more. Okay. So what we want to show is that J, M, J is included in M prime. And for this, I will take Y, Z in M, and X prime in M prime. And I make the following computation. Z, J, Y psi naught times X prime of psi naught, it's equal to J, Y psi naught times Z star X prime psi naught. That means X prime Z star psi naught, because they commute, which is equal to X prime star. It comes, X prime star, it comes in front. X prime star, JY, psi naught times J delta power 1/2 Z psi naught. That is just S of Z psi naught. Okay. Which is equal to, further, I put J in the other side. But putting J in the other side, it changes the order in the scalar product because it's conjugate linear. So that this is delta 1/2 Z psi naught. That means this thing which remains here, times J X prime star J Y psi naught. Okay. Not what I can write here. I can write, but this is not trivial. It's because we already proved that J M prime J is in M. So that element in here, this J X prime star J, is an element in M. So that I can write it as being S star, S of Y star J X prime J psi naught. It is S, the conjugation, the adjunction of this element. So that is this thing times delta 1/2 Z psi naught. It's equal to this. And then this is equal to delta power 1/2 Z psi naught times delta power minus 1/2 this J Y star J. Okay, delta minus 1/2 J is this S in here. Y star J times X prime. J psi naught is psi naught. so that this is psi naught simply. And what I get finally, it is the fact that this is z psi naught. Delta power 1/2 and with delta power minus 1/2 they cancel because I pass in the other side by adjunction. And what I get is j y star j x prime of psi naught. And finally, this is equal to j y j is the adjoint of this thing times z psi naught x prime psi naught. Once I have this thing, yeah, it's good. Now, this is dense in H. So that what we get that z j y psi naught, it's equal to what is there. It is j y j z psi naught. Fine. And now the same trick. You put j y j of x z naught is equal to x z j y psi naught. It's equal to x times j y j z. You see, j y j, it's this one. J of psi 0 is psi 0. I take it and I put it here because I know already that j y j is in M prime. Ah, no. No, no. No. I'm sorry. xz. This is xz j y j psi naught. Okay. This is x times j y j z psi naught. This is because of the original relation in here, not because of the commutation. And now you cancel this because it's dense in the Hilbert space. And you see that j, y, j commutes with every element in M. So j, y, j belongs to M prime. So that it's already obtained the fact that j, M, j, it's equal to M prime. And tomorrow we will see the continuation of this. So the proof of Van Dahl is a short proof, a very short proof. The technical element, which is that residual theorem, is you will see. I ask you a quarter of an hour in the afternoon to show the operator theoretical lemma. It's just the residual theorem. And tomorrow I will continue with showing that delta to power it. It's clear. Put here a j and a j again and get a j in here. You get here M prime. And so you see that j with j and j with j cancel, and this shows that delta power minus it, M prime, delta power it is equal to M prime. And then you go to M also. Okay, thank you.